Hello friends, welcome to SR Physics Academy. Today we are going to discuss about Introduction to Quantum Mechanics. First we will discuss about origin of classical mechanics. By the end of 19th century, all the known laws of physics were easily understandable by the Newtonian mechanics. Maxwell equations describing electricity and magnetism and on statistical mechanics describing the state of large collections of matter. So here many of you know would be familiar with concept from classical mechanics. Presumably you know what is meant by independent degree of freedom, generalized coordinates, constraints, generalized momentum, phase space. Some of you might even be aware of the richness of structure of the phase space. Now, when it comes to quantum mechanics, this concept could undergo some alternation. The alternation we are not obvious under history of quantum mechanics is as revealing as it was dramatic. However, the observation of some experiment could not be explained on the basis of these known laws. It failed to explain motion in atomic particles like electron, proton, etc. We would cite many examples for the failure of classical physics. Blackbody radiation, specific heat of solid at low temperature, theory of atomic structure, spectrum of hydrogen, photoelectric effect, Crompton effect. This already you know that. The above mentioned experimental phenomena gave two important conclusions. Energy is condensed. Light radiation exhibit particle-like behavior. So here, now the quantum mechanics. The quantum mechanics is a study of very small things. It explains the behavior of matter and its interaction with energy on the scale of atomic and subatomic particles. Classical physics predicted that heated objects emit instantly all their heat into electromagnetic waves. Here, Maxwell calculation shows that the radiation rate went to infinity as the electromagnetic wave went to zero. That means here we can say ultraviolet spectroscopy. Here, what is here ultraviolet spectroscopy is also called Rayleigh-Jeans spectroscopy. Here, the study of the law of black bodies and the failure of classical mechanics to describe them helped establish the foundation of classical mechanics. Here in this graph, that means here ultraviolet spectroscopy refer to a paradox that emerged in scientists' understanding of the way light is emitted by black bodies that exist in thermal equilibrium. It was also called Rayleigh-Jeans spectroscopy, was the prediction of late 19th century or early 20th century classical physics that an ideal black body at normal. Okay, here the black body at thermal equilibrium will emit radiation in all frequency ranges, emitting more energy as the frequency. So here Planck solved the problems by postulating that energy of EM electromagnetic wave is emitted in the form of quanta with energy E equal to h nu. As progress in the science field was happening, Maxwell's suggestion about the wave nature of electromagnetic radiation was helpful in explaining phenomena such as interference, diffractions, etc. So here Many concepts in quantum physics are very dramatic. It is very difficult for the human mind to comprehend it, at least. It was at that stage in history, and I am talking about the end of the 19th century, where most classical laws were pretty well understood. The first thing that was very different when it comes to quantum physics is that fact an object can be thought of as a wave and as a particle. This is normally called wave particles or duality photoelectric effect, and this demonstrates the particle nature of object. However, in this case, he failed to explain various other observations such as the nature of emission of radiation from hot bodies, photoelectric effect, ejection of electrons from a metal compound when a electromagnetic radiation strikes it, the depends of heat capacity of solid upon temperature, line spectra of atoms, especially hydrogen. So here photoelectric effect, we can say that here light falls on a metal plate and electrons are emitted. Now if the light were thought of as electromagnetic wave and electron come out of this metal plate, you would normally expect the energy of the electron that comes out to be related to the intensity of the incident light. In other words, we can say that the intensity of the incident light changes. You could expect energy of the electron to change. For example, for light of very low intensity, then you would expect low energy. Electron for light of high energy, it expects high energy electron. But that is not what happened, and he explained only if the basis of corpuscular theory. In other words, we can say that light is a collection of particles, namely photon E equal to h nu. Here nu is we know that frequency of the light and h is the Planck's constant. So now, according to Planck's quantum theory, different atoms and molecules can emit or absorb energy in discrete quantities only. The smallest amount of energy that can be emitted or absorbed in the form of electromagnetic radiation are known as quantum. So here the energy of the radiation absorbed or emitted is directly proportional to the frequency of the radiation. That we know that from lower energy to higher energy. So E equal to h nu. Here E equal to energy of the radiation, h equal to Planck's constant 6.626 into 10 power minus 34 joule and nu equal to frequency of radiation. Interestingly, Planck has concluded that these were only an aspect of the process of observation and emission of radiation. They had nothing to do with the physical reality of the radiation itself. Later, in the year 1905, famous German physicist Albert Einstein also reinterpreted Planck's theory to further explain the photoelectric effect. He was of the opinion that if some source of light was focused on certain material, that can eject electron from the material. Basically, Planck's work led Einstein it determined that light exists in discrete quanta of energy or photons. Here, the building on the de Broglie approaches, modern quantum mechanics was born in 1925 when the German physicists Werner Heisenberg, Max Born and Pascal Jordan developed matrix mechanics and the Austrian physicist Erwin Schrödinger invented wave mechanics. So in 1926, the Schrödingers proposed a wave equation that described the manners in which Matter waves change in space and time. It is a key element in quantum mechanics. Thanks for watching.